Welcome to my all-in-one chemistry video. This is for the 9:1 new specification. Now, as always, don't forget that I sell my perfect answer revision guides on my website, which is www.sciencewithhazel.co.uk. If you click on this card, you'll be able to go and purchase yourself a copy. It is available now in all 3 sciences. So if you enjoy my videos and you enjoy the way in which I describe and explain things, that is where you will find a distillation of my videos. You'll also find information about revision courses if you're keen on attending, school licenses and private tuition. However, enough about that, let's get started. What is activation energy? Remember, that's the minimum amount of energy required for a reaction to occur. So why does increasing the temperature increase the rate of reaction? Well, remember, the particles have more kinetic energy, they collide more frequently and they have more successful collisions. Why does increasing concentration increase rate of reaction? Because there are more particles in the same volume, collisions occur more frequently. Why does increasing the surface area increase the rate of reaction? Well, that's because you have more frequent collisions. So do get the term frequency of collisions in your answer, and that will really help. Obviously, if you decrease pressure, concentration, temperature, surface area, the opposite will be true. What is a catalyst? This is asked in both biology and chemistry. A catalyst is a substance which speeds up a reaction without being used up. And in terms of chemistry, you want to say it offers an alternative reaction pathway with lower activation energy. What is a reversible reaction? Well, it's where the products can react together again to produce the original reactant. What is the dynamic equilibrium? Now, that's the hard process, and we'll need to talk about that a bit later, but it does just pop up here. Dynamic equilibrium is where both the concentrations of the reactants and products don't change and that the forward and reverse reactions are taking place at the same time. Marble chips are mainly calcium carbonate. A student investigated the rate of reaction between marble chips and hydrochloric acid. Figure 9 shows the apparatus the student used. So we've got marble chips and hydrochloric acid happily fizzing away in this conical flask, and then a delivery tube taking the gas, which we know must be carbon dioxide due to the marble chips. And also it says it on the diagram, and that's going to be added to the measuring cylinder so we can then work out the volume of carbon dioxide produced. Anyway, I digress. Complete and balance the equation for the reaction between marble chips and hydrochloric acid. Never mix your symbols here. Symbol and words, we can see straight away that we need symbols because of calcium chloride. So first of all, we've got hydrochloric acid, which is HCl. The formula of marble chips is limestone, so that's CaCO3, and then that produces carbon dioxide and water. You do just need to learn this, and then just have a quick check and see if it's balanced. No, it's not balanced, so we need 2 hydrochloric acids. Have another look and we can see that it's balanced. 9.2, table 4 shows the student's results. I feel a graph coming on. On figure 10, plot these results on the grid, draw a line of best fit. So make sure you're occupying as much of the graph paper as possible. They've told us that time in seconds needs to go along the x-axis. So looking back at the numbers, I've got to plot a 0 here, and then to make sure it all fits, I'm going to go each little square will be 30. Oh, look, I'm running out of space already. Oh my god. And we need to get up to 270. Obviously do it better than that, but you know, iPad. I can't resist adding those bits. Then it's tricky because the volume of gas is so tiny. You kind of need to ignore the little noughts and just look at it as being 30, 46, 52, 65, and that will help you plot. So we need to go from 0 to 0.08, which is the equivalent of kind of 80. So I'm just looking at my axis. So if I go 10, 20, 30, 40, 50, 60, 70, 80, yeah, that fits. And then just when I label the axes, I need to make sure I actually reintroduce those insane numbers of significant figures. So I've plotted all the points. You need to use a nice sharp pencil for this, and now we're going to try and draw a good line of best. Oh, it's too high! Oh, the iPad. Oh, make sure your line goes to your points. So imagine I've shifted that down by ½ centimetre. Now I'm going to have to stay on this page because the next question reads, sketch a line on the grid in figure 10 to show the results you would expect if the experiment was repeated using 20 grams of smaller chips. So smaller chips means a large surface area, which means an increased rate of reaction. And I just need to double check. Yeah, so we're expecting the same volume of gas to be produced, so we need to make sure that the line finishes in the same place. So we're going to see a steeper line but that it will end in the same place, which is why it'll look like this, and we're labelling it A. 9.4, explain in terms of particles how and why the rate of reaction changes during the reaction of calcium carbonate with hydrochloric acid. So we know right at the beginning the rate of reaction is going to be very high, but then as the reaction continues, the rates of reaction will decrease. The reason being that the acid particles will be used up, which means that their concentration decreases. With decreased concentration, we get less frequent collisions, and therefore the rate of reaction decreases. Another student investigated the rate of reaction by measuring the change in mass. Figure 11 shows the graph plotted from the student's results. Use figure 11 to calculate the mean rate of reaction up to the time the reaction is complete. Give your answer to 3 significant figures. So in order to do this, you need to look at the mass of the mass that was actually lost. So you need to have a look at here where it crosses the line, and then where that line levels out, which is here. So this is quite hard. So you've got 152.5 at the top, and then if you read the bit at the bottom very carefully, you'll see that it's 150.3. So if you take those two numbers away from each other, you get a mass loss of 2.2 grams, and then in order to work out rates of reaction, you need to divide that by the time taken, and that's where you have to look along this axis in order to see where the reaction actually stopped, which was actually at 270. So when it equaled out at the first point, so that's 270 seconds. So then you do 2.2 divided by 270, and that gives you an answer which is 0.00815. Use figure 11 to determine the rate of reaction at 150 seconds. Show you're working on figure 11. Okay, scrolling back up then, so 150 seconds, which is here. We need to work out the tangent. So you're going to use your ruler and draw a nice straight line on top of that. That's horrible, and because it's a rate of reaction, we need to work out the gradient, which is y over x. So m equals y over x. And then you're going to have to read off that x-axis again. So you'll find that this is horribly drawn again, iPad, but you'll find that the mass lost was approximately 0.35, then divided by the time in seconds, which was approximately 50, and that will give you an answer which is 0.07. They do allow a range of answers here because everyone will draw that tangent slightly differently. I just want to quickly talk you through reaction profiles. So you might end up with being given a graph that looks like this, so energy on the y-axis, progress of reaction on the x-axis, and then they could easily give you a level for the reactants, 1 for the products. Incidentally, this is an exothermic reaction because we're going down, which means it's a negative enthalpy change. And then they could show you this sort of thing, and they'd be like, right, label the activation energy. So remember, that's the minimum amount of energy required for a reaction to occur. So you'd have to label from the reactants to the top of that graph line, and you'd label that activation energy. And then another thing they could ask you to do is draw the profile when you've got a catalyst. So because the catalyst lowers the activation energy, you simply need to draw a similar curve but lower. And that would be the, sorry, it's such a mess, that would be the activation energy with a catalyst. So just to be clear that it makes it lower. Now we're looking at equilibrium. So with the term exothermic, let's define it. First of all, it means the release of heat energy. And remember that more energy was needed to make the bonds in the products than was needed to break the bonds in the reactants. So looking at endothermic reactions, you'll see the opposite. So heat energy in this case is taken in, and more energy is required to break the bonds in the reactants than was needed to make the bonds in the products. Other terms we need to know: activation energy. This is simply the minimum amount of energy required for a reaction to occur. How do catalysts work? Well, we know from biology that they speed up the rate of reaction without being used up. In terms of how they work, it's because they provide an alternative reaction pathway with lower activation energy, and I'll show you some energy profiles so you can actually see that lowered activation energy. So chemical equilibrium now, we are looking at reversible reactions here, so be aware of this special arrow. This is your reversible arrow, and it tells you that the reaction is happening in both the forward and backwards direction, and what that really means is the reactants react to produce the products, as we're used to seeing, but then the products will fall apart effectively and produce the reactants again. So these aren't ideal conditions when we're talking about industrial processes, because it basically means you make very little of the product that you're after, and we use the word yield to describe the amount of product produced. So let's start by looking at what a dynamic equilibrium means. Now, first of all, the word dynamic means that the reactions are ongoing, which means that the forward and reverse reactions are occurring at the same time. Because it's equilibrium, it means they're occurring at the same rate, and that there is no overall change in the concentrations of reactants and products. And this is only true if it occurs within a closed system, and a closed system is simply one where nothing is allowed to escape. So no gases can leave and no more reactants get added. It remains a sealed vessel. So looking closer at dynamic equilibria, let's look at the effect of a catalyst. Now, you must notice that a catalyst simply increases the rate of reaction. We know this, I've just said it. It does it by providing an alternative reaction pathway with lower activation energy. Note, it does not alter the position of equilibrium, so it doesn't increase the yield of the products. It keeps the position of equilibrium in the same place, it just increases both the forward and reverse reactions equally. A summary now of what happens when we choose to alter reaction conditions. So remember, we can alter the position of equilibrium if we change both the temperature and pressure. As I've already said, the catalyst has no effect. Remember, when a reaction is exothermic, the whole reaction gets hotter, and when it is endothermic, the whole reaction gets cooler. So if we start by increasing the temperature, we know we need to oppose the change, so we're going to favour the reaction, which results in a decrease in temperature, which is why increasing the temperature favours the endothermic reaction. And that means that the position of equilibrium will shift to favour that endothermic reaction. So if you have an equation and the delta H says that it is positive, we know that the forward reaction is therefore endothermic. So increasing the temperature will favour the forward reaction. Decreasing the temperature will favour the exothermic reaction, and the position of equilibrium will shift to favour that. And if this is sounding complicated, don't worry, because we're going to use the Haber process as an example to help us understand it. Looking at pressure now, if you increase the pressure, what happens is equilibrium position will shift to favour a decrease in pressure, so it will shift to the side with a fewer moles of gas, and you count the number of moles by looking at the big numbers in front of the formulae. Decreasing the pressure will favour the side with increased number of moles of gas, so position of equilibrium will again shift. Hydrocarbon chemistry, this is a massive topic. We're going to be looking at the alkanes, the alkenes, complete and incomplete combustion, but let's dive straight into it with the alkanes. So remember, the general formula of the alkanes is CnH2n plus 2, and you can use that formula in order to work out the molecular formula of any alkane. So for example, what is the molecular formula of the third alkane? Subbing in 3 to that equation gives you an answer of C3H8. You must be able to name the first 4 alkanes, and you want to use monkeys eat peanut butter in order to help you with this. So methane, monkeys, eat, ethane, peanut, propane, butter, butane. So methane, ethane, propane, butane. What is the formula of butane? C4H10. Now remember, alkanes and alkenes are both hydrocarbons, so you need to provide a perfect definition of a hydrocarbon, which is that it is a compound containing hydrogen and carbon atoms only. If you don't say only, you don't get the second mark. Well, someone's much happier now with her head buried in her fur. With the alkenes now, what is the general formula of the alkenes? It's CnH2n. List the first 4 alkenes. Well, remember, with an alkene, they're very special because they have a C double bond C, which means methane doesn't exist because you need a minimum of 2 carbon atoms to have an alkene. So therefore, technically, the first alkene is ethene, followed by propene, butene, pentene. What is the formula of propene? C3H6. You must be able to draw all the displayed formula. Now, key terms you need to know is the difference between saturated and unsaturated. We say that alkanes are saturated because all the carbon bonds are single, whereas alkenes are unsaturated because they contain a double carbon bond. How do we actually get hold of the alkenes and the alkanes? Well, we get them from crude oil, and fractional distillation has to occur in order to separate that crude oil into all the different length hydrocarbons. So if they ask you a 4 marker on how to carry out fractional distillation, you're going to say that you heat the hydrocarbons until they evaporate, They rise, cool and condense, and because there's a temperature gradient within that fractionating tower, you find that the short chains condense at the top where it is coolest, the long chains condense at the bottom where it is hottest. You need to know the order of fractions in the fractionating tower starting from the top. So those are refinery gases. Remember that they're used in central heating, followed by petroleum, which is used as petrol in cars or fuel in cars. Then you have kerosene, which is airplane fuel, diesel, used in lorries and buses, fuel oil, which is used as ship fuel, and lastly bitumen, which is used for road surfacing. Other words you'll need to know are things like viscosity. Remember, that's how runny a substance is. So the more thick a substance is, the more viscous it is. Volatility, that's how easily something turns into a gas. So if they ask you for a comparison of the volatility, viscosity and colour of bitumen and petrol, you'd say that bitumen has a darker colour, it is more viscous and it is less volatile than petrol. Now, why are we bothering with all this? Well, it's obvious because we're trying to get fuel that can be burned to supply our cars, etc. with energy so they can run. So what is a fuel? Well, it's a substance which releases energy when burnt. Now, depending on how much oxygen is available will dictate if you've got complete or incomplete combustion. So with complete combustion, you have a plentiful supply of oxygen, which means the byproducts produced are carbon dioxide and water. Whereas with an incomplete combustion, you have insufficient oxygen and carbon monoxide and water are produced instead. What's the issue with carbon monoxide? Well, first of all, it's poisonous, and what that means is how it actually works is that it combines irreversibly with the hemoglobin in your red blood cells and therefore prevents oxygen being transported. Obviously, there are still issues with carbon dioxide. Carbon dioxide is a greenhouse gas leading to global warming, sea levels rise, etc. So neither of these situations is ideal. There are other pollutants that you get from burning these hydrocarbons. In car engines, for example, the high temperatures found will cause the nitrogen and the oxygen to react. And what happens is nitrogen oxides are formed, they dissolve in water, and that can fall as nitric acid, which is acid rain. Again, you'll get acid rain from sulfur, and this time sulfur impurities in the original crude oil cause sulfur dioxide to be produced. That falls as acid rain. What are the issues relating to acid rain? Well, first of all, it damages limestone buildings. We must say limestone. Secondly, it makes lakes and rivers too acidic. And lastly, it damages trees. They often like to ask you how you test for a saturated or unsaturated hydrocarbon. So what you're going to do here is add bromine water, and with an unsaturated hydrocarbon, you'll see orange colour turning to colourless. And that's because the bromine's added itself to the original hydrocarbon, so it doesn't exist anymore. And here's the equation showing that. With saturated hydrocarbons, you won't see any reaction. Getting more technical again, so what is a homologous series? Remember, it's a family of compounds with the same functional group. So something like the alkenes, they all have a C double bond C. The alcohols will all have an OH group. This question is about organic compounds. Hydrocarbons can be cracked to produce smaller molecules. The equation shows the reaction for the hydrocarbon C18H38. So we can see C18H38 being broken down into lots of shorter hydrocarbons. Which product of the reaction shown is an alkane? So remember, alkanes obey this general formula, which is CnH2n plus 2. So either those things do have to obey it. So the way we do that is we can check them out by doing C6H14. So that would be C6 and then H, and let's make sure, so we would do 2 times 6 is 12 plus 2 is 14. Yeah, it obeys the formula, which is why D, or option 4, is the answer. And obviously you would go through and check the others just to show you this one doesn't work, because 2 times 4 is 8, and if you add 2 you get 10, but that formula isn't C4H10, it's just C4H8, which is why it's not an alkane. Table 1 shows the boiling point flammability and viscosity of C18H38 compared with the other hydrocarbons shown in the equation. Which letter A, B, C or D shows the properties of C18H38, how they compare with the properties of the shorter hydrocarbons. So first of all, boiling point is obviously the temperature at which it boils, so the larger the molecule, the higher the boiling point. C18H38 is the largest molecule mentioned, which is why its boiling point must be the highest. In terms of flammability, that's how readily it sets alight. the larger the molecule, the less flammable it will be. So we're looking for lowest on flammability. Finally, viscosity is how readily the substance flows. So the more viscous a substance is, the thicker it is and the less readily it flows. So obviously larger molecules will flow less readily and therefore they'll be more viscous. So you're looking for boiling point highest, flammability lowest, viscosity highest, which is why the answer here is A. The hydrocarbon C4H8 was burnt in air, incomplete combustion occurred. Which equation correctly represents the incomplete combustion reaction? Incomplete combustion requires you to know that carbon monoxide and water are produced, so that brings down your options to A and B, and actually no, we're just looking for water, not hydrogen, which is why the answer here is B. A small cylinder butane C4H10 contains 5 kilograms of butane. Write a balanced symbol equation for the complete combustion and what would the maximum mass of CO2 that would be released. So let's start with our balanced symbol equation. So we've got C4H10 and we know we're burning it in oxygen, it's combustion, so we're going to add O2. Because it's complete combustion, we're going to make carbon dioxide and water as our products, and then it's a matter of balancing it. So we've got 4 carbons on the left hand side, so I'm going to write a 4 here. And then I'm just going to add up how many, oh yeah, there's 10 hydrogens on the left hand side, so we need to put a 5 here, and then we need to work out how many oxygens there are on the right hand side. So we've got 4 times 2, which is 8, plus 5, which is 13, so we need 13 divided by 2, why am I doing it on my calculator, which is 6.5 oxygens over here. You might want to make it all integers, so that's whole numbers, so you could double it, so it would become 2 C4H10 plus 13 O2 forms 8 CO2 plus 10 H2O. Now in terms of working out the mass, I'm going to do it the way I've always done it, so we're going to turn it into a table. By the way, I redrew it so that we've got whole numbers because it will make it easier. So we write mass, MR, moles as the table. We look at the question, we're looking for the mass of CO2, so we're going to put an X under CO2. We know the mass of butane, it's 5 kilograms, but I'm going to convert that to grams, so that becomes 5,000. Then it's a matter of working out the MR of butane, so carbon has a mass of 12, you get that from the periodic table. We're going to do 12 times 4 plus 10 times 1 because we've got 10 hydrogens and 1 is the mass of hydrogen. Add that up and you get an answer which is 58. Let's work out the MR of carbon dioxide. So carbon is 12, oxygen is 16. We need to multiply that by 2 because of the fact that it's CO2, so it becomes 44. Then we're going to use this triangle, which is mass is number of moles times MR to work out the number of moles. We can see that that's therefore mass divided by MR. So to work out the moles of butane, we're going to do 5,000 divided by 58, which gives us 86.2068. So we want to keep that number nice and unrounded so we don't introduce rounding errors. Then it's a matter of comparing the mole ratio here. So it's 2 to 8. So we've got 4 times as much carbon dioxide. So we effectively take this number and times it by 4, which gives us a value of 344.827586, blah blah blah. And then we're finally after X, so we're going to use our formula triangle again. We're looking for mass, so therefore it's number of moles times MR. So we're going to do 344.827 times 44, which gives us a value which is 15,172 grams. Now we're moving on to chemical analysis. So we're going to start with defining a pure substance. So that's a substance made up of only one type of thing. So that could be all the same element or it could be all the same compound, but nothing else can be mixed in there. You need to know the definition of a fixed point, so that is the boiling or melting point of a specific element or compound. Now we need to define formulation, so remember that is a useful mixture made up of set proportions. I really hate this topic, it's so random. Like the next question, what is paint made out of? I don't know, who cares? Is that even chemistry? But it's actually made out of a pigment, which is actually the colour of the paint. It's made up of a binder that helps the paint stick to an object. And lastly, it's made up of a solvent, which enables the binder and the paint to mix properly. Another fascinating thing you need to know is what is washing up liquid made out of? And I'm just summarising this as quickly as possible. So obviously there'll be water in there. There's fragrance because you're washing a liquid, smells of lemon or cherries or whatever. It contains rinse agent and also surfactant, which actually helps break down those fat molecules that stick to your pans if you fried an egg or something. And lastly, colouring, because something like very liquid is often very bright green, and that's not a very natural colour. What is this about? Now we're going to talk about chromatography. So remember, chromatography is used to separate different inks or dyes or food colourings. You do need to know a little bit how it's set up. So remember, what you do is you get a piece of filter paper or blotting paper, use a pencil line to draw a reference point, then you dot your inks along that reference point, and then you dip the very end into water, and as the water soaks up, it will draw the dyes up and they'll separate and you can see what's in there. Now, why is it drawn in pencil, that reference line? Because obviously if it was drawn in ink, that would rise too and totally screw up your findings. They like you to calculate the RF value, so that's quite a simple equation. You just need to do RF equals distance moved by dye divided by distance moved by solvent, and in this case it would be water. So you'd use your ruler to measure those lines and then you'd pop it into the equation. 7. A student investigated food dyes using paper chromatography. This is the method used. Put a spot of food colouring X on the start line, put spots of 4 separate dyes A, B, C, D on the start line, place the bottom of the paper in water and leave it for several minutes. Figure 5 shows the apparatus the student used. So this is paper chromatography. It's used to separate coloured inks, dyes, food colourings, etc. And if you remember, the water soaks up the blotting paper, dragging the ink with it, and we can work out lots of things from the results. Write down 2 mistakes the student made in setting up the experiment and explain what problems one of the mistakes would cause. Okay, the thing that's really jumping out at me first of all is that they say that the start line is drawn in ink. No, 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 big no. That has to be drawn in pencil. The reason being that when the water soaks up, it would cause the ink line to spread as well. So imagine the mess that would make. So the start line needs to be drawn in pencil. The second thing is the water really only should be touching the very bottom of the paper. It's blotting paper, it's filter paper, so that water will move anyway. The moment you dip it straight in the water, it means that the spreading of inks will occur far too quickly, and then you again wouldn't be able to see the results. Another student set up the apparatus correctly. Figure 6 shows the student's results. The result for dye D is not shown. Calculate the RF value of dye A. Give your answer to 2 significant figures. So first of all, it's important that you know the equation for the RF value. So remember, RF equals distance moved by ink divided by distance moved by solvent or water. So in that case, you need to do, for the distance moved by ink, get your ruler and literally measure this exact distance here. And then for the distance moved by the water or the solvent, get your ruler and measure this line here, which will give you 2 numbers. And those numbers are 2.8 for the distance moved by ink A, 8.2 for the distance moved by the solvent. Pop those into your calculator and you'll get a value which is 0.34 to 2 sig fig. Do make sure you follow the instructions given. Dye D has an RF value of 0.80. Calculate distance that dye D moved on the chromatography paper. This is a reverse calculation. So if we say RF equals distance moved by ink over distance moved by solvent, so we know the RF value we've been given is 0.8. We're looking for the distance that D moved, so that will be X, and we're going to divide it by the distance moved by the solvent, which we just measured, which is 8.2. And then in order to work out what X is, you need to times everything by 8.2, and that will give you a value which is 6.6. Explain how the different dyes in X are separated by paper chromatography. 4 marks, so 4 separate points. You want to talk about the fact that the solvent moves through the paper for the first mark. Then state that different dyes have different solubilities in the solvent for the second mark. Therefore, they have different attractions to the paper for the third mark, and then they're carried to different distances for the 4th mark. So that's really a step-by-step guide as to how paper chromatography actually works. Next up, we're talking about tests. So we're looking at tests for positive and negative ions and more generic tests. So we'll start with the generic test for gases. I think I've already mentioned that the test for hydrogen is that a lighted splint pops. Now do use the exact wording that I'm using because I'm using the most concise, succinct wording possible to make sure you have to learn as little as possible. So to that end, we're going to look at how oxygen is tested for. So this time you want a glowing splint, so one that you've blown out and is now you're kind of blown out, but it's still smoking and glowing at the end, and that's going to relight in the presence of oxygen. Carbon dioxide, you're going to bubble that through lime water, and if it's carbon dioxide, it will turn that lime water cloudy. The test for chlorine gas is that it bleaches damp litmus paper. Tiny bit now on the Earth's early atmosphere and how it's changed to become the atmosphere of today. So obviously the plants photosynthesized, which means they took in carbon dioxide and then released oxygen, so O2 levels rose, CO2 levels decreased because carbon dioxide got locked up in sedimentary rocks and also inside the ocean itself. You saw the oceans and seas actually form due to water vapor condensing. Remember, the continents came together to form a large supercontinent called Pangaea, and the volcanoes became smaller, and that's due to the formation of the Earth's crust. Let's talk about the atmosphere of today in terms of the relative amounts of different gases. Remember, we have approximately 80% nitrogen, approximately 20% oxygen, and there's a tiny percentage made up of carbon dioxide, water vapor, and noble gases. We've already talked about the crude oil topic, but now we're going to talk about how those fossil fuels originally formed. So they formed over millions of years from the bodies of dead sea creatures, which got crushed under intense pressure and heat, causing layers to come together, and before you know it, fossil fuels were formed. And this is the issue we have today, is that they are running out, and there is no way we have enough time to actually produce them all over again, because the whole process takes millions and millions of years. The issues we have though in terms of banning those fossil fuels, it's all to do with climate change and global warming. So the issues we have when we do complete combustion, when carbon dioxide is released into the air, remember that carbon dioxide is a greenhouse gas, so it contributes to global warming. That rise in temperature causes the ice caps to melt, so you see a rise in sea level, and then due to that you see a flooding of low-lying land, so loss of biodiversity, which means all the vegetation and animals are killed that live on those areas. You see a change in bird migration patterns, because birds will tend to fly across large parts of the world in order to get food, but all this climate change will cause them to not know where they're supposed to be going, and you'll see extreme weather. So all those storms that we were aware of, Jose, Maria, Harvey, I'm trying to think of all the different names of the hurricanes that were this season. This is all due to climate change, so why Trump is denying it is just disgusting. But yeah, climate change is real, guys, and we need to do something about it. Anyway, this video isn't about me banging on about climate change. I'm going to move on now. I'm going to talk about the different types of pollution formed by our various human activities. So I've already mentioned carbon dioxide. I previously mentioned the fact that sulfur impurities in crude oil, nitrogen and oxygen reacting in car engines forms nitrogen oxides, sulfur dioxides. That forms acid rain, which when it falls damages limestone buildings, destroys trees, makes lakes and ponds too acidic. You've got things called particulates, which is like soot particles that come from diesel engines, which cause global dimming. Now we're going to list some examples of resources which are finite, which means that they will run out. So that's your fossil fuels, it's your crude oil, and it's your metal ores, so things we use in iron extraction, aluminium extraction, for example. If we wanted to list some renewable resources, we could talk about the fact that sugarcane and wood, they can both be grown time and time again, as long as we have the space to grow those plants. Next topic, sewage treatment. Lovely. So first of all, what are the steps involved in water purification? You can write loads on this, but I want to make sure you're learning as least as possible for the most marks possible. So simply, all you have to do is filter to remove solids, and secondly, you need to add chlorine to kill bacteria, and we know that that is a super essential step. If they ask you what desalination is, it means the removal of salt from the water. Oh, another really bizarre bit, which is describing the process of reverse osmosis in water purification. Remember that membranes are needed to separate the dissolved salts from the salty water, and secondly, remember that high temperatures are needed, so it's a very high energy cost process. Faces! Lyra! So to this end, what is the disadvantage of using distillation to purify water? Kitten! Oh my goodness, twice in one video! So cute! So kitten, what is the disadvantage of using distillation to purify water? Well, it needs lots and lots of energy, doesn't it? Which means it's a very expensive process. Kitten. Kitten, are you really muddy? No, you're quite... Hey now. Help everyone with their chemistry. Okay, bye. So if they ask you about sewerage treatment, the 3 main steps, it's very similar to water purification. So you need to filter to remove solids, you need to add bacteria to actually feed on the sewerage, and you need to carry out sedimentation, which is actually the process which makes sewerage sludge. It's hard to say sewerage. I think I'm saying it wrong, more and more wrong the more I say it. Going on to the extraction of metals, I've already looked at the extraction of aluminium using electrolysis, but now we're going to look at the extraction of copper. Remember, it's a very useful metal. It's used for lots of our wiring because it's a very good conductor. 2 main ways then. Number 1, smelting, which means roasting that copper ore with oxygen at very high temperatures. The second way is more complicated. It is using electrolysis, and what we do is we add sulfuric acid in order to make copper sulfate solution, which we can then electrolyze to obtain the copper. However, more and more, increasingly, we're finding that copper reserves are running out, so we're turning to other methods to actually obtain our copper. One of those methods is called bioleaching, the other one is called phytomining. This is very useful where there's very low grade copper, and what that means, it means poor quality copper. It means soils that contain very small amounts. But what happens is in bioleaching, the bacteria feed on that copper, and in phytomining, the plants absorb the copper ions in their roots. And then what you can do is that you burn those plants, and then with the ash you dissolve that in sulfuric acid and then carry out electrolysis on it. More about the environment then. What does LCA stand for? Life Cycle Assessment. I've never taught this in my life, and I've been teaching this for a while. What is the purpose of LCA? To look at the environmental impact of products, services and processes. So what are the main steps involved in LCA? I suppose it does make sense. It's raw material extraction, manufacture, the use, reuse or maintenance of a substance, and recycling and waste management. Whew. I could not ever be bothered to learn that. That is just so extra. Thank you so much for watching my video. Well done if you made it to the end. Don't forget you can buy my Science with Hazel Perfect Answer Revision Guides on my website. They're available right now at www.sciencewithhazel.co.uk.